Hello everyone. Today we are going to continue with our discussion on the topics of limits. In my previous video, you would have already seen the concept of limits, the algebra of limits, and the basics behind it. Today, let us just do a quick recap and proceed further. So we have seen that if you find a value of a function in the immediate neighborhood of any point x equal to a, then that value is called the limiting value, and it is basically used in cases where the function is not defined at that point. Otherwise, for all other functions which are defined at a point, means if the value of a function is defined at a point, then limit as x approaches a fx is the same as the value of the function at that point. Then we had seen that for a polynomial, again, since the function is always defined, the limiting value is the same as the value of the function at that point. The problem arises when we are dealing with a rational function. And before that also we had done the algebra of limits, and in that we had done the various properties, means of the operations of addition, subtraction, multiplication, division, and multiplication by a constant. We have seen that whether you first find do the operation on the functions and then find the limits, or you first find the limits individually and then perform the operation, the result is the same. Now let us consider the limits of a rational function. We know that a function is said to be a rational function. Let's say a function fx is said to be a rational function if it can be written as in the form hx over gx. Okay. Now, where hx and gx are both polynomials, in x, or we can say that they are both functions of x. Now, suppose we have to find the limit as x approaches a of this function fx. Now here hx and gx being polynomials, the limit as x approaches a hx is equal to ha. It is defined and is equal to ha. Similarly, limit as x tending to a gx is also defined and is equal to ga. Now, if we have to find the limit as x approaches a of fx, we'll get it as limit x approaching a hx over gx. By algebra of limits, it will come out to be hx over limit x tending to a gx. And as we had discussed in the previous video also, this is defined so long as this denominator is not equal to 0. As we already are aware that division by 0 is not possible. Okay, now in this, while finding the limit of a rational function, there are 4 cases which arise. Case 1 is that when both HA and GA are not equal to 0. And so clearly we can see that limit x tending to a would be fx would be equal to this, which is both equal to HA over GA. And also the value is also defined. So basically then the limit x tending to a fx is nothing but the value of the function at a. Second case is when HA is equal to 0, GA is not equal to 0. Now in this case also the value is also defined, because division by of a 0 by a non-zero number is allowed and is equal to 0. And so the value is also defined and the limiting value is also defined, and both are equal. So limit x tending to a fx is equal to the value of the function at a, and which is equal to 0 by a non-zero element, which is 0. So both the value as well as the limiting value is equal to 0. The third case is when when HA is not equal to 0 but GA is equal to 0. Here neither the function nor the limit is defined. Reason being, here what is the limit? Limit x tending to a fa would be equal to limit x tending to a hx over limit x tending to a gx, which will be equal to something non-zero upon 0. Now dividing anything by 0 is not defined, as we all are aware. So these are the first three cases where in the first two cases, since the function itself is defined, so limit doesn't have a separate role to play. It is the same, like limit exists and is equal to the value of the function. Third case, neither the function exists nor the limit is defined. Now it is the fourth case which is of interest to us as far as limits are concerned, and the fourth case is that both HA and GA are equal to 0. Now, so that when you find the value of the function of fx at a, it is 0 by 0 form. Now, it is in this category that limit comes to our aid mainly. And what we do is, now here again there are three cases. Now first of all, let's see if it is 0 by 0 form, and we know that FA is HA over GA, where HA and GA are both polynomials. Now we know by factor theorem that if a polynomial is 0 at any value of x, then x minus a will definitely be a factor of that polynomial. Only then we can say that it is 0 at that point. Okay, so by factor theorem we have HA can be written as x minus some factor into some polynomial. Let's say some polynomial, let's say polynomial 1, which is left out. Okay, and this x minus a could be in some power. Now similarly, GA also, or GX actually, not GA. Now GX can also be written as some power of x minus a, let's say m, and into some polynomial 2 which is left out. So that when we find in the, of course the value of the function is not defined. FA is not defined at all because you can't cancel 0 with 0. But in the limiting value, what we have is fx can be written as limit x tending to a of hx upon limit x tending to a of gx will be equal to limit x tending to a x minus a raised by l into some polynomial 1 upon limit x tending to a of x minus a raised power of a into some another polynomial 2. Now here again there are three cases which arise. Now here first of all what we see is x is not in the limiting case. X, no matter how small or how close x is to a, but still x is not equal to a, and so x minus a, no matter how small it is still not equal to 0 and can be cancelled. Now again three cases arise. Now here case 1 is when L is great. First case 1 is when L is equal to m. Then clearly both the factors, they get cancelled. So limit x tending to a fx will be equal to limit x tending to a x minus a polynomial 1 upon limit x tending to a x minus a raised power of m polynomial 2. This gets cancelled and you are left with polynomial 1 upon polynomial 2, which is something non-zero quantity, and that is the limiting value. Though the value does not exist, but the limiting value exists, and it is, you just substitute x equal to a in these two polynomials. Like for example, if we have it as, we have to find limit x tending to 2 x square minus 4 upon into x, let's say, plus 1. Now it can be written as limit x tending to 2 x minus 2 x plus 2 upon x minus 2 x plus 1. This and this gets cancelled because the power of both numerator and denominator, power of x minus 2 is the same. And so simply the limiting value of this minus 4x minus 2x plus 1 will be equal to, you will substitute x is equal to 2 in both numerator and denominator. You will get 2 plus 2 over 2 plus 1, which is 4 by 3, which is the answer, and the limit exists and is equal to this. The second case would be when L is greater than M. That is, in that case, x tending to a fx will be equal to limit x tending to a x minus a some polynomial 1 upon x minus a raised power m some polynomial 2. When you cancel it, you are still left with some power L minus m of x minus a. And when you substitute, this comes out to be 0. Right? So the limit exists and is equal to 0. For example, you can take limit x tending to, let's say, 2, and we have x minus 2 whole square into x plus 2 upon x minus 2 into x plus 1. This gets cancelled. You are still left with one x minus 2 factor. It comes out to be 0 by something non-zero, which is equal to 0. And the third case is when L is less than M. Then in this case, what we have is limit x tending to a fx will be limit x tending to a. You will have x minus a raised by L some polynomial 1 upon x minus a raised by m some polynomial 2. Now here, this gets cancelled and you are left with m minus L. So when you substitute, you will get something non-zero upon this is 0, which is not defined. So it is this category of a 0 by 0 function in which neither the value nor the limit exists. Okay, and for example, you can take it as limit x tending to 2. Let's say x minus 2, x squared minus 4 upon x minus 2 whole square x plus 1. So you can write it as limit x tending to 2 x minus 2 x plus 2 upon x minus 2 whole square x plus 1. This gets cancelled. You are still left with a factor x minus 2 in the denominator, and when you substitute, you get something non-zero upon 0, which is not defined. So it is in this category that neither the value of the function nor the limit is defined. Now with this, we can do the first 9 questions except for the 6th one of the exercise 13.1. Like for example, let's quickly do one question and then we proceed further. Let's do question number 8 of exercise 13.1. We have to find the limit as x tends to 3 of x raised power 4 minus 81 upon 2x square minus 5x minus 3. We can clearly see it is 0 by 0 form. When you substitute x equal to 3 in the numerator and denominator, it comes out to be 0 by 0 form, and so not defined. So now here, so clearly x minus 3 should be a factor of both numerator and denominator. So let us solve it further. We can write it as x square minus 9 into x square plus 9 whole upon, let's factorize it. It will be minus 6x plus x minus 3. So when you solve further, what we get is x tending to 3. Now again, this can be factorized as x minus 3, x plus 3, x squared plus 9 whole upon. Now this comes out to be, you put these two together, 2x, you are left with x minus 3 plus 1, x minus 3. And when you write it, you get x tending to 3. X minus 3, x plus 3, x squared plus 9 whole upon 2x plus 1 into x minus 3. In the limiting case, we are able to cancel this x minus 3 factor. Now simply substitute the value of x as 3. We get 3 plus 3 into 9 plus 9 upon 3 into 2 is 6 plus 1, which comes out to be 6 into 18 upon 7, which is equal to, this is 48, 4 carried, 108 by 7, which is the answer. So in this way, we can solve any and every rational function. Now we come to another category of questions, which is question number 6 of the exercise 13.1. Let's see, the function is somewhat like x tending to 0, x plus 1 raised to power 5 minus 1 upon x. Now this clearly is again 0 by 0 form. Now in order to do such kind of questions, we will be first doing one result or one theorem, which will come in very handy. One way of doing it is expanding it by binomial theorem and then solving it. But this also becomes very unwieldy in case the power is a fraction. We are not able to do it. And even if the fraction power is a natural number, but a big natural number, then also it becomes too unwieldy to handle. So we have a very simple theorem which comes to our aid in such cases and helps us solve these questions very easily. So now we do theorem number 2, which says that given any positive number n, we have limit x tending to a, x raised to power n minus a raised to power n over x minus a equal to n a raised to power n minus 1. I mean, if you remember, if you can remember it, it's well and good, but we will just quickly do the derivation of this so that it will get registered in your minds as to how we have got this result. We are not doing it on our own. It is actually that we get this result. Now, let's start with limit x tending to a, x raised to power n minus a raised to power n over x minus a. When you put the value of x as a, it is 0 by 0 form. So the value of the function is not defined. So again, by factor theorem, we know that x minus a needs to be a factor of this. Now this clearly you can see that x minus a is a factor, but over here also using factor theorem, you have done it in your previous classes as to how you can write x raised to power a n minus a raised to power n in terms of x minus a times something. But still, if you don't recall, we can just quickly derive it and see that by long division you get multiply the quotient. If you write x raised to power n minus 1, you will get x raised to power n minus a n raised power x raised power of n minus 1. On subtracting, this gets cancelled. You are left with a x raised power n minus 1 minus a raised power n. Again, to bring in this factor, you have to multiply it by a x raised power n minus 2. A x raised power n minus 1 minus a squared x raised power n minus 2. This gets cancelled, and now what we get is we get back a squared x raised power n minus 2 minus a raised power of n. Again, multiply it by a squared x raised power n minus 3. So we get a squared x raised power n minus 2 a cube x raised power n minus 3, which again on subtraction this gets cancelled. You are left with a cube x raised power n minus 3 minus a raised power. Proceeding in this manner, it gets totally divided when the last term becomes a raised power of n minus 1. And so you can write it as limit x tending to a x raised power n minus a raised power n upon x minus a is equal to x tending to a x minus a times x raised power n minus 1 a times x raised power n minus 2 a square times x raised power n minus 3 plus towards the end you have a raised power n minus 1 whole upon x minus a. In the limiting case, this x minus a gets cancelled with this. Now these are n terms starting with x raised power 0 to x raised power n minus 1. Now when you put the value of x as x approaches a, you get this comes out to be a raised power n minus 1, a raised power n minus 1, a raised power n minus 1, a raised power n minus 1. These are n terms. And so we get the formula as limit x tending to a x raised power n minus a raised power n upon x minus a is equal to n times a raised power n minus 1. Now let us see how this result can be used to solve our questions. So let's take one example. It is limit x tending to 1 x raised power 15 minus 1 upon x raised power 10 minus 1. And the result which we have to use is x raised power n minus a raised power n over x minus a is equal to n a raised power of n minus 1. Now here if you see, only the numerator is the same. Denominator is something different. But again you can write so here we need x minus a also. Here x tends to a. This is x raised power 15 minus 1 can be written as 1 raised power 15. We need the denominator as x minus 1. Now as x approaches 1, it is x minus 1 is non-zero, and we can divide both numerator and denominator by something non-zero. And it comes out to be limit x tending to 1 x raised power 15 1 raised power 15 upon x minus 1 whole upon x raised power 10, and here I can write it as 1 raised power 10 upon x minus 1. So this becomes equal to now limit of the numerator upon limit of the denominator. That is 15 1 raised power 15 x minus 1 upon limit x tending to 1 x raised power 10 1 raised power 10 x minus 1. When you substitute, what we get is, it is n. N is 15 here, into a is 1. 15 minus 1 is 14. Whole upon, this is 10. A is 1 raised power of 9, which is 15 by 10, which is equal to 3 by 2. Similarly, we have now the question number 6 which we had started with. Question number 6 is limit x tending to 0 x plus 1 whole raised power 5 minus 1 upon x. When you put x equal to 0, this comes out to be 0 by 0 form. Now, so what we do is, now if you just compare it with this result, whatever x tends to, that is what you have to have in the with a minus sign here. So now what we have is, and that is what in the denominator we should have. If it is x raised by n minus a raised by n, we should have x minus a in the denominator. Here we have x plus 1. So can we write it as, you add 1 and you subtract 1. Now it is in the same form as expected. Now what we do is, let's put x plus 1 as t. So now, so what does this become? This becomes t raised power 5 minus 1 upon t minus 1 and in the limiting case. Now it is exactly in the same shape as this result, but again here the limit is of x and the function is in terms of t. So we need to change the limit also in terms of t. So as x approaches 0, t approaches, now you write 0 plus 1 which is equal to 1, and so you can write t approaching 1, this. Now it is exactly in the same format as the theorem, and we get it as n, that is 5, into a is 1, 4 raised power of 5 minus 1, that is 4, which comes out to be 5. Exactly on the same lines we have another example, which is x tending to 1. X tending to 0, 1 plus x square root minus 1 upon x. Exactly on the same lines, this is 0 by 0 form. Now, though this can be expanded by binomial, no matter even if it is long, but at least you can expand it by binomial theorem. This one, the power being half, we can't even expand it by binomial theorem, and so this theorem is the only one which can be used to solve it. And exactly on the same lines, we can put 1 plus x as t, as x tends to 0, t tends to 1, and this comes out to be limit t tending to 1, t raised by half minus 1 upon t minus 1. Now here this can be written as raised by half, answer will be half into 1 raised by half minus 1, which is again equal to half, because 1 raised by anything whether positive or negative is 1. So with this you can do these kind of problems very easily. Thank you.